Hello everyone, I'm Peng Li from Georgia Institute of Technology. I'm going to present our work, FuzzyJoin, auto-program fuzzy similarity joins without labeled examples. This is a joint work with collaborators from Microsoft Research. FuzzyJoin, also known as similarity join integer resolution, is an important operator that takes two tables as input and identifies record pairs that refer to the same entity from the two tables. For example, here we have two tables of persons' names. We can see that the first record in the left table and the second record in the right table refer to the same person. The fuzzy join can also be performed on tables with multiple columns. For example, here we have two tables of movies with three columns including name, director, and description. We can see that the first record in the left table and the second record in the right table refer to the same movie. FuzzyJoin has been extensively studied in the database community. Nowadays, there are many commercial systems that can perform FuzzyJoin efficiently on very large tables. However, we find that most of FuzzyJoin systems are not easy to use. This is because these systems often have a great number of configurations, and they often ask users to carefully set up these configurations. For example, in Microsoft Excel, it has a total of 19 configurable options across 3 dialogs. Among these 19 options, 11 of them are binary, such as whether to enable edit transformation or not. Even with these binary options, there are already over 2,000 discrete choices. There are also 8 continuous configurations, such as similarity threshold, which has infinite number of choices. Different configurations may produce totally different fuzzy joins. In order to produce high-quality fuzzy join, these configurations must be set up properly. We summarize the common fuzzy join configurations into 5 classes, including preprocessing, tokenization, token weights, distance function, and distance threshold. Combining the options in the first 4 classes, we can get what we call a join function, which specifies a method to compute the distance score returned to records. For example, we can choose lowercase 3 gram IDF weight and Jacquard distance as a join function. Applying this join function onto records, we can get a distance score. By comparing the distance score with the distance threshold, we can determine whether two records are matches or not. So, a join configuration consists of a join function and the distance threshold, and the configuration space is then defined by the combination of all join functions and all distance thresholds. A single join configuration is often not enough to produce high-quality fuzzy joins. This is because in real-world datasets, different types of strain variations are often present at the same time. For example, in the following dataset, L1 and R1 differ by 1 extra token. Jacquard distance is suitable for this type of variation. But Jacquard distance is not able to join record pairs like L3 and R3 that differ by few characters. Edit distance is more suitable in this case. So in order to capture different types of strain variations, it's often necessary to use multiple configurations at the same time and take the union over their joining results. Setting up these configurations is not trivial. Not surprisingly, we have seen a lot of user questions in Excel user forums asking how fuzzy joins can be configured appropriately, such as how to set token weights, how to set similarity thresholds, how to choose distance functions, and how to use multiple configurations. For professional users, they can inspect input data and use their experience to choose the suitable configuration. But for less technical users, they have to try a large number of configurations, or just use the default configuration, which may not produce good result. So this motivates us to propose the auto-program FuzzyJoin framework. In our framework, besides 2 input tables, users only need to specify 1 parameter called precision target. The precision means the fraction of produced fuzzy joins that are correct. For example, if users require the produced fuzzy joins to have precision at least 0.9, in other words, among all produced fuzzy joins, users want at least 90% of them are correct joins, then they can set this precision target to be 0.9. Different from other fuzzy join systems that ask users to configure the program, our framework will automatically select the suitable configurations from the configuration space. The selected configuration can produce fuzzy joins that meet the precision target expectation while maximizing fuzzy join recall, which is the number of correct joins. Our framework can be formally defined as follows. Given 2 input tables and a user-specified precision target, we would like to select a union of configurations from the configuration space that maximizes the recoil while keeping the precision above the target. The recoil is defined as the number of correct joins produced by the selected union of configurations. The precision is defined as the fraction of produced joins that are correct. This problem can be written as a constraint optimization problem. We call it recoil maximization FuzzyJoin problem. To solve this problem, there are two major challenges. The first challenge is that the precision or recoil is unknown. Actually, we just need to know one of them, because by definition, we can compute the recoil using the product of precision and the number of produced joins. The second challenge is that even if we know the precision and the recoil, this problem is NP hard, because we need to select a subset from the space, and the number of possible subsets is exponential to the size of the space. To overcome the first challenge, we leverage the fact that in most FuzzyJoin tasks, one of the input tables is a reference table that contains few or no duplicates. For example, in the well-known modular integer resolution repository, we find that 66% of the datasets have one table that contains exactly no duplicates, and 90% of the datasets have one table that contains less than 5% duplicates. This shows that the reference table is prevalent in real-world datasets. Let's refer the L table as a reference table and the R table as another input table. We don't know the precision of our joins produced by a join configuration because their ground truth is unknown. To estimate the precision, our idea is to join the L table with itself using the same join configuration. Because L and R are similar in nature, we can expect that the precision of LR joins should be similar to the precision of LL joins. Because the L table has almost no duplicates, the ground truth match of each record should only be itself, and any other joins are incorrect. This suggests that the less the LL pairs joined, the higher the precision is. Let's see an example. This is a dataset of Super Bowl games. If we use edit distance not greater than 1 as a join configuration, which means the records will be joined if they differ by no more than one character, we will get many incorrect LR joins, such as L1 R1, L2 R2, and L3 R3. In comparison, if we use containment distance not greater than 0 as a join configuration, which means the records will be joined if one record is a subset of another, we can get many correct joins such as L5 R5 and L6 R6. Now let's use the join configurations to join the L table with itself. As we can see, the low precision join configuration can produce more LL joins than the high precision one. This verifies our intuition that the less the LL pairs joined, the higher the precision is. Based on this intuition, we propose a method to estimate the precision for every single join produced by a join configuration, representing how likely this join is to be correct. Assume that R1 is a record in the R table. When we use the join configuration to join R1 with the L table, we get a record L1, which is identified as the match of R1. To estimate the precision of this join, just like what we did in the previous slides, we can join the record L1 with the L table. Because the record L1 and R1 are similar in nature, the precision of joining the L table with R1, namely the precision of L1 R1 join, should be similar to the precision of joining the L table with the record L1. Because L table almost has no duplicates, L1 should only be joined with itself. So the precision can be computed as 1 over the number of records in the L table that can be joined with L1. Let's see an example to understand how this works. Assume that we have 3 joins produced by a join configuration. To estimate the precision of the join L2 R2, we use the join configuration to join L2 with all the records in the left table. We find that there is only one record in the left table that can be joined with the L2, so the precision of this join is 1. Similarly, for the join L3 R4, we find that there are 2 records in the left table that can be joined with L3, so the precision is 1 over 2. For the join L4 R5, there are 3 records in the left table that can be joined with L4, so its precision is 1 over 3. After we compute the precision of every join, the overall precision of the join configuration can be computed by averaging the precision of every join, which is 0.61 in this example. Similarly, if we use a union that consists of multiple configurations, we can also compute the precision of the union using the average precision over all the joins produced by the union. We observe that in real-world datasets, the left table may be incomplete, where some of the left records can be missing. This can affect our estimation. For example, in the previous example, if the record L5 is missing, the precision of L3, L4, and L4, L5 will be increased because there are less LL joins. This would make the precision of the join configuration overestimated. To solve this problem, we double the distance threshold in the join configuration when performing LL joins. For example, if the join configuration is edit distance not greater than 1, when we perform LL joins, we use edit distance not greater than 2. Intuitively, using the double distance threshold can join more LL pairs, which makes our method more robust to incompleteness of the L table. In our paper, we provide more explanation of using double distance with geometric interpretation and triangular inequality. It is also shown empirically from our experiments that using double distance indeed make our method more robust. Given that the problem is NP hard, we propose to use grid algorithm to solve it efficiently. The idea is to start from an empty set. At each iteration, we would select just one configuration from the space and add it to the union. This will be repeated until the estimated precision below the given precision target. Now the question is, which configuration should we select at each iteration? Since our goal is to maximize recall while preserving the precision, intuitively we prefer configurations that can produce more true positives at the cost of introducing less false positives. Therefore, we define the profit of the union as the ratio of true positives to false positives, which can be computed using the estimated precision of the union. Then, at each iteration, we will select the join configuration that maximizes the profit of the union. When joining datasets with multiple columns, for each column, we can compute a distance score using join functions. For example, for the movie dataset with 3 columns including name, director, and description, we can get 3 distance scores from different columns between 2 records. Our observation is that different columns usually have different importance for fuzzy joins. For example, in this dataset, name and director are more important, but description is less important. Therefore, we introduce column weights to represent the importance of each column. And the distance between 2 records can be computed as the weighted sum of distance scores from different columns. For example, here we can assign name, director, description with column weights 0.6, 0.4, and 0 respectively. Then the distance score between the 2 records can be computed using weighted sum, which is 0.04. But the column weights cannot be directly incorporated into our configuration space. This is because its complexity is exponential to the number of columns. For example, assume that each column weight can take 10 possible values from 0 to 1. Even with 3 columns, we can have 1,000 different possible column weights in the space. To overcome this issue, our idea is to use only a subset of columns instead of using all columns. Because we observe that in most datasets, there are many columns such as description that are not useful for FuzzyJoin. To select the most important columns, we propose a forward column selection algorithm, which is analogous to forward feature selection algorithm in machine learning. Our algorithm starts from an empty set of joining columns, and iteratively expands this set by adding the most important column from the remaining columns. Because we are maximizing the recall, the importance of a column can be determined by the resulting recall after adding it, which can be estimated using the method we introduced before. The algorithm terminates when the recall cannot be improved by adding an extra column. As we will show in the experiments, in most datasets, the algorithm usually terminates with 1 or 2 columns, which are already enough to produce good results. The column selection algorithm significantly reduces the number of columns used, but we still need to determine the column weight for each selected column. Because we are maximizing the recall, and the if approach is to use grid search to find the column weights that produces the highest recall. But as we mentioned before, the space of possible weights is exponential to the number of selected columns. To solve this problem, we propose an efficient column weight search algorithm. Our intuition is that the relative importance between 2 columns are usually not affected by adding new columns. Therefore, at each iteration of column selection, after adding a new column, we only need to search the weight for the new column, while keeping the relative weights of old columns unchanged. Let's use an example to show how this algorithm works. Assume that in the previous iteration, we found that when assigning a name and director with column weights 0.6 and 0.4 produces the highest recall. At the current iteration, we want to add a new column, description. Instead of trying all possible weights for every column, we only perform research on the weight of the new column. For example, we try 0.1, 0.2, and so on for the weight of description. For name and director, we just scale their weights, but keeping their relative weights unchanged, which is still 0.6 to 0.4. It can be proven that using column selection and column weight search algorithm, the complexity of column weights becomes quadratic to the number of columns, which is acceptable in practice. We evaluate our approach on a variety of datasets. First, we constructed a new benchmark with 50 single-column FuzzyJoin datasets using DBpedia. This dataset involves various integer types, including persons' names, football leagues, political parties, and so on. Second, we also evaluate our method on 8 multi-column datasets that are commonly used in the integer resolution literature. We compare our approach with 5 unsupervised and 3 supervised methods. For supervised methods, we use 50% of the whole data as the training data. For our method, the configuration space consists of 140 different join functions and 50 different distance thresholds. We set the precision target to be 0.9. We evaluate the quality of fuzzy joins using standard precision recall score and PRUC score. This is the average performance on 50 single-column datasets. As we can see, the average precision of our method is 0.886. which is very close to the precision target 0.9. Based on either the average recall or average PRUC score, our method significantly outperforms all other baseline methods, including the supervised methods that use 50% data as training data. We construct several adversarial test cases to test the robustness of our method. First, for each dataset, we add some irrelevant records to the right table. As we can see, even when 80% of records in the right tables are irrelevant, AutoFJ can still achieve an average precision of around 0.84, with recall almost unaffected. Second, we randomly removed some records in the left table. As expected, the average precision decreases as more and more records are missing in the left table. But even with 30% of records removed, our method can still achieve precision above 0.8. And this is the running time of our method compared to other baselines. We can see that AutoFJ is on average 2 to 3 times slower than ECM and Excel, but faster than 0ER, Magellan, and FuzzyUzi. This is the average performance on 8 multi-column datasets. As we can see, based on the recall, our approach remains the best method on average in the multi-column fuzzy joins. Based on the PRUC score, it outperforms all other unsupervised methods and achieves comparable performance compared to supervised methods. Also, we can observe that the columns selected by our algorithm are indeed informative attributes. For example, on Rotten Tomato IMDb dataset, which is a mobile dataset, the name and director are the most important columns, with name being more important. This shows the effectiveness of our column selection and weight search algorithms. To conclude, we propose an auto-FuzzyJoin framework with the following features. First, it is automatic. Users only need to provide 2 tables and a precision target. The FuzzyJoin programs will be configured automatically. Second, it is unsupervised, which means it does not require users to provide any labeled examples of matches or non-matches. Third, it can produce high-quality fuzzy joins. As we have shown in the experiments, our method can even outperform strong supervised baselines using labeled examples as training data. Fourth, it is robust. As we have shown in the experiments, our approach can be robust to various adversarial test cases. Fifth, our approach is explainable. Compared to black box FuzzyJoin methods, our approach produces FuzzyJoin programs that are described using configuration options like preprocessing method, tokenization method, distance function, and distance threshold, which are easy for practitioners to understand and verify. Finally, our approach is extensible. The configuration space in our framework is transparent to users and can be easily extended with new configuration options like new distance functions. That's all. Thanks for listening.